So last episode ended with the CPU half of the container story fixed. Go 1.25 reads your C group quota by default now, and I told you the memory half was next. The half that as of Go 1.26 still hasn't shipped. Here's what that looks like. A Go program in a 512 megabyte container doing something deliberately boring. Hold 260 megabytes of live data, churn garbage 1 megabyte at a time, and it dies, narrated by its own GC trace. The last collection is GC7, finishing with 262 megabytes live, and then the collector just stops. The heap climbs 447 megabytes, then 497 megabytes, and numGC sits frozen at 7. The whole way to exit code 137. The collector wasn't broken, it wasn't behind. By its own arithmetic, the next collection wasn't due until the heap roughly doubled to about 524 megabytes. And container ceiling was 512 megabytes. The kernel doesn't negotiate two governors running the same process without ever speaking. A GC trigger that's proportional to your live heap and a kernel limit that's absolute. Today, the collision on tape, the one environment variable that fixes it, and what the famous 80% rule actually buys you. So let's get the Go side precise, because the whole story is one formula. The Go GC guide gives the trigger exactly. Target heap equals to live heap plus GC roots times Go GC over 100, where the roots, Go routine, stacks, and globals are only in the formula as of Go 1.18. Now take the default Go GC of 100 and a small root set that collapses to collect when the heap doubles past the live set. Not a fixed budget, not a fraction of machine, a ratio. And you can watch it work with the GC trace turned on. Grow towards 200 megabytes live, and the heap goals walk 4, 9, 18, 36, 72, 142, 280. Textbook doubling while the program keeps running alive. The trace prints 3 numbers per collection: heap at trigger, at the end of mark, and live afterward. And that last one seeds the next goal. On a laptop, this schedule is a background detail. In a container, it's a countdown, computed by something that has no idea the walls exist. Now the kernel side, which is brutally simple. The Kubernetes memory limit becomes C group v2's memory.max, and the usage occurs in memory.current, which counts the whole C group. Anonymous memory, page cache, kernel structures like entries, inodes, TCP socket buffers, not just what your allocator asked for. The kernel docs state the end game plainly. If the C group's memory usage reaches this limit and can't be reduced, the OOMKilled is invoked in the C group. And notice the can't be reduced. The kernel reclaims what it can first, so clean page cache gets squeezed before anyone dies. But when reclaim isn't enough, what it sends is sick kill. Exit code 137, which is 128 plus signal 9. No warning, no handler, nothing your defer statements will ever see. So run the collision back with the mechanism visible. In the container, the goals walked 4, 9, 20, 40, 84, 166, 328 megabytes, same doubling shape, slightly different values because the churned garbage rides along with the growing live set. Then the GC7 at 0.142 seconds into the run finished with the 262 megabytes live. Feed that into the formula and the next target lands roughly around 524 megabytes above the 512 ceiling. From that moment, the process was unkillable by its own GC and guaranteed to be killed by the kernel. It churned through another 235 megabytes of garbage. SYs climbed to 505 and the OOMKilled closed the account. While the runtime at its last stat line still believed it had 27 megabytes of runway. And it's worth being precise about what this isn't. Not a leak, not a spike, not a fragmentation. The runtime scheduled its next collection past the container's limit because nothing ever told it there was a limit. Now the rescue. Same binary, same container, one environment variable added GOMEMLIMIT equals to 410 megabytes, which is 80% of 512. Quick honesty note, the OOMKilled ran grew until it was killed. This one churns a fixed 2000 iteration so it can terminate and show an exit code. Same per iteration allocation pattern, different run lengths. And this isn't the folklore version where the GC gets more aggressive as you approach the limit. The mechanism is blunter. The limit lowers the goal. Go GC's proportional math still wants roughly 524. The memory limit computes its own ceiling of about 392 megabytes. That's 410 megabytes minus the run's non-heap memory. The smaller number wins. Every collection from GC8 onwards triggers at 388 megabytes like a monotone. 22 collections instead of 7. Sys parked at 401, 2000 megabyte of garbage churn. That's roughly 6 times longer than the unprotected run survive. And then the word you want in your logs: survived. Exit code 0. Go mem limit's been there since Go 1.19 by the way, and it composes with Go GC rather than replacing it. It's respected even with Go GC off, a combination the GC guide calls maximization of resource economy, which in my books retries the heap ballast hack. But here's the part that stings after the last episode. Go 1.25 made Go Max Procs C group aware by default, and that's no memory equivalent as of Go 1.26. The proposal to derive Go mem limit from the C group limit, issue 75164, is still open. The community stopgap is a library called AutoMemLimit, which defaults to 90% of the C group limit. Until the proposal lands, CPU configures itself and memory is your job. The docs call GOMEMLIMIT a soft limit. The word soft is doing two very different jobs, both demonstrable. Phase 1. The limit yields rather than thrash. Retained 450 megabytes live under the same 410 limit, so the live set alone exceeds the ceiling, and the runtime's response is to overshoot. Sys settles at 465 past the limit while it collects almost continuously. 247 collections in about a third of a second, back to back. What makes that survivable is a documented cap. Go GC CPU is limited to roughly 50% over a window of 2 times Go Max Procs CPU seconds. So in the worst case, the program slows down by at most 2x. This run made progress the whole time and exited 0, degraded but alive. Phase 2. It's not a shield. Ask the same setup to retain 560 megabytes more than the container itself. The Go mem limit changes nothing that matters. 84 futile collections killed at about 507 megabytes of heap, exit 137 anyway. A live set bigger than the box is provisioning problem, and no environment variable fixes provisioning. A seatbelt, not a bigger car. So what does GOMEMLIMIT actually count? The doc defines the counting of all memory map managed and not released by the Go runtime. Effectively sys minus the released heap, and that includes Go routine stacks. Park 2000 Go routines on a channel, and the runtime metric shows 16.2 megabytes of stacks, about 8.3 kilobytes apiece. Sitting inside the total the limit governs. So no, you don't budget stack outside Go mem limit. What the doc exclude is what the runtime never touches. The binary's own mappings, memory from C code via CGO, raw memory maps, and kernel memory. And the C group, meanwhile, counts things Go has no API for. Write a 300 megabyte file from inside the container. Memory.current jumps from 0.9 megabytes to just shy of 316, nearly all of it page cache. While the Go runtime's view of the world doesn't move, the saving grace is that clean page cache is reclaimable. That can't be reduced clause again. So the kernel squeezes it before invoking the OM killer. And cache alone rarely kills you. Dirty pages, temp fs, are the dangerous kind, charged exactly the same way and not droppable. So how much headroom below the container limit does GOMEMLIMIT need? The wild offers 3 answers, and they are not the same number. The GC guide says leave additional 5 to 10% for memory sources the runtime is unaware of. Auto mem limit shifts 90% as its default, and the folk practice says 80, which is what the rescue run used. But that's no primary source for 80% rule. I looked. Treat it as a conservative starting point, not a law. And I'll own a correction. The older version of the blog posted claimed 5 to 10% of your memory goes to allocator overhead. Measured, that didn't hold up. A heap around 453 megabytes, the gap between sys and heap alloc was about 12 megabytes, 2 to 3%, not 5 to 10%. On this workload anyway. So check the memory classes matrix yourself. The real budget question isn't the allocator stack at all. It's your non-runtime memory, the page cache, your IO generates, CGO, mmap. That's what the headroom is for, and it's measurable, so measure it. The two knobs stay complementary. Go GC controls how often the GC runs proportionally, that's your CPU versus memory trade-off. Go mem limit is the ceiling the goal can't cross for the danger zone near memory.max. Set both as environment variables, not in code, so you can tune without rebuilding. And the workflow upgraded from vibes to measurement is 5 steps. Baseline with Go GC at 100 and no limit in a dev container. Then measure under real load. Runtime matrices for Go's side, memory.current for C groups. Because the gap between them is your invisible memory. Budget the container limit from peak runtime memory plus that gap plus margin. Protect with GOMEM limit at 80 to 90% adjusted by what you measured. And if GC CPU runs too high, raise Go GC and let GOMEM limit be the backstop. The whole harness is under 150 line in the post. With one gotcha that silently falsifies results. Keep the retained set in a package level variable, because in a local one, liveliness analysis lets the GC collect it after its last use, and your rescue passes because the live set quietly vanished, not because the limit worked. So the takeaway, and unlike the last episode, the runtime won't do this one for you. Set Go mem limit on every containerized Go service today as an environment variable. Start at 80 to 90% of the container's limit, then let measurements, not the ratio, pick the final number. The white headroom is exactly your non-runtime memory. CPU got its C group aware default in 1.25, memory's proposal is still open. And hope is not a pacer. And keep the two failure modes straight. They need different fixes. If num GC froze while the heap climbed to the kill line, that was a scheduling gap. Go mem limit solves it outright. If the GC was firing constantly and you still got 137, your live set doesn't fit in the box. And the fix is memory or architecture, not the tuning. A seat belt, not a bigger car. There's a bill for all this though. The rescue traded 7 collections for 22, and GC frequency is the latency you pay somewhere else. Especially once Go 1.26's new default collector, green tea, enters the picture. The full write-up is linked below. traces and harness included. And if this series is earning its place in your feed, you know where the subscribe button is. Next episode, GC pauses and latency, what all the extra collecting costs you and where the pauses hide.